Welcome to The Explainer. Today, we're tackling something huge, an invisible force that, well, it pretty much shapes our entire world. Magnetism.
I mean, have you ever really thought about it? It seems so simple, but believe it or not, that invisible pull has its roots deep, deep down, right inside every single atom.
So what is magnetism? At its absolute core, it's all about moving charges. That's it. Anytime you've got an electric charge that's moving, boom, it creates this incredible force. A force that can either pull things together or push them apart.
You know, we usually run into magnets in two main flavors. You've got your natural ones, like lodestone, which is basically a rock you can find in the ground. And then you have the artificial ones we make, the bar magnets, the really powerful stuff we engineer for things like motors and even MRI machines.
Okay, so whether it's a natural rock or some high-tech magnet, where does that force actually come from? To find the answer, we've got to go smaller. No, I mean much, much smaller.
Because it turns out the secret isn't in the magnet as a whole thing you can hold. The real origin story of magnetism, it all starts with a single atom. That tiny, tiny building block of matter, that's where all the power comes from.
So picture this. Inside every single atom, you've got electrons just whizzing around the nucleus, right? Well, that electron has an electric charge, and it's moving. What does that create? A teeny tiny loop of electric current. And here's the kicker. It's a fundamental rule of our universe that any electric current, I don't care how small, generates a magnetic field.
So what does that mean? It means, and this is the crucial point, that every single atom in the universe is basically a microscopic magnet. Seriously, it's got its own little north and south pole. The fancy term for it is an atomic dipole. Okay, but wait a second. That leads to a pretty obvious question, right? If every single atom is a tiny magnet, why isn't a block of wood magnetic? Why can't I stick my coffee cup to the fridge? Why isn't, well, everything magnetic?
Well, the answer is all about alignment, or more accurately, a total lack of it. See, in most stuff, all those little atomic magnets are pointing in completely random directions. Think of it like a huge, disorganized crowd where everyone is just facing a different way.
And that is the whole game. In a non-magnetic material, all that chaos means the tiny magnetic fields just cancel each other out. The net result? Zero. Nothing. But when you can get them all to line up and point in the same direction, suddenly all their individual forces add up, creating one strong, powerful magnetic field that we can actually feel.
So how materials react being told to align, that's where things get really interesting. It turns out we can basically group everything into one of three what I like to call magnetic personalities. First up, you've got the rebel. These are your diamagnetic materials like water or copper. When a magnetic field comes near, they actually push back a tiny bit. They weakly repel it. Then you have the follower. These are paramagnetic materials like aluminum. They'll sort of go along with the field, but they're not super into it. They're just weakly attracted.
But then there's the superfan. This is the one we all know and love. We're talking about ferromagnetic materials. This is the big one.
So what makes materials like iron, nickel, and cobalt so special? Well, their atomic magnets are already team players. They naturally form these big groups called domains, where they're all pointing the same way. So when an external magnetic field shows up, it doesn't try to convince one atom at a time. It convinces these entire domains to flip and align. The effect is huge. That's what creates that strong attraction, and it's why these materials can become permanent magnets themselves. Okay, so rebel and superfan are fun, but scientists need to be a little more precise, right? They use two key measurements to describe these personalities. Now, the names might sound a bit technical, but the ideas are simple. One measures how much a material wants to be magnetic, and the other measures how well it supports a magnetic field. Let's start with magnetic susceptibility. The best way to think about this is as a material's magnetic enthusiasm. Is it positive? That means it's super eager to get in line with the field. Is it negative? That means it's a rebel. It's actively pushing back and opposing it. The other metric is relative permeability. This one measures how easily magnetic field lines can actually travel through something. You can think of it like a magnetic superhighway. If it has a high value, that means the material is great at concentrating those field lines, making it a fantastic pathway for magnetism to flow through.
And this chart really brings it all together. You can see the rebel diamagnetic materials have that small negative susceptibility. They're not enthusiastic. The follower paramagnetic materials, slightly positive. But look at the superfan ferromagnetic materials. Their susceptibility is large and positive, and their permeability is way, way bigger than 1. They are the true magnetic superhighways.
You know, there's a quote that just nails this whole idea. It says, "The properties of materials are determined by the dance of electrons within their atoms." And that's it, isn't it? The huge difference between a bit of copper that barely pushes a magnet away and a piece of iron that grabs on for dear life, it all comes down to that intricate dance of electrons.
But that dance can be broken up. What's this number, 1,000 Kelvin? Well, that is the Curie temperature for iron. If you heat a piece of iron past that point, all that heat energy just creates chaos. The atoms shake around so violently that those nice organized domains completely fall apart. The superfan loses its enthusiasm and the iron starts acting just like a casual follower. It becomes paramagnetic.
So, after all that, from tiny atomic orbits to these magnetic superfans, what's the key takeaway here? What should you really remember?
It's this. That amazing force holding a magnet to your fridge starts with nothing more than the movement of an electron. That simple motion turns every atom into a tiny magnet. And a material's whole personality, whether it's a rebel, a follower, or a superfan, it's all decided by one simple thing: how well those tiny atomic magnets decide to line up.
And that leaves us with one last, really cool thought to chew on. Since an atom's magnetism is born from an electron going around in a loop, it has to create both a north and a south pole. They're a package deal. You can't have one without the other. And that's why, if you take a bar magnet and snap it in half, you don't get a lonely north pole and a lonely south pole. Nope. You just get 2 brand new, smaller magnets, each with its own perfect north and south pair. A perfect little echo of the atoms they're made of.